Hello, lovely students. Welcome back to Intermolecular Forces. This is going to be part two of two. So, Intermolecular Forces 2, the search for more forces. If you haven't watched the previous video, I'd like you to go ahead and take a second to go back over to that other ed puzzle. The first two guiding questions of our lesson on intermolecular forces are answered there. The guiding questions: what are intermolecular forces and how can we tell if a molecule is polar? We need to know both of those things to be able to figure out what kinds of intermolecular forces are present in a substance. So really quickly, to be able to answer this question, we need to be able to answer this one. And the answer to this question is, how can we tell if a molecule is polar? Remember that just because a molecule has polar bonds doesn't mean that the entire molecule is polar. To be able to have a polar molecule, regardless of what the bonds look like, the molecule has to have what's called a dipole moment. The dipole moment happens when all of the charges of the various bonds kind of go in the same direction. So in the case of water, H2O, we have two oxygen-hydrogen bonds. The hydrogens are less electronegative than the oxygen, so what happens is all of the electrons start to kind of converge and hang out around the oxygen, giving it a slightly negative one end and a slightly positive other end. So here's a quick little review of what we had. How do we know if a molecule is polar? A molecule is polar if it has a dipole moment. It has a dipole moment if the individual bonds are polar and they pull in the same direction. There are lots of different kinds of intermolecular forces, and you could talk to about 5 different chemistry teachers and they'd all have a slightly different way of thinking which ones are the most important. But for our class, we're going to focus on 3: dispersion forces, dipole-dipole forces, and a special kind of dipole-dipole force called the hydrogen bond. Without going into a lot of detail about what dispersion forces are, the 2 things that I want you to know about them is they're the only kind of intermolecular force that nonpolar molecules have. The other thing that I want you to know about dispersion forces is that they're the weakest kind of intermolecular force. The next thing we're going to talk about is dipole-dipole forces. Dipole-dipole forces are a intermolecular attraction between the delta positive or the slightly positive end of one molecule and the slightly negative end of another molecule. And remember, we say slightly negative and slightly positive, and we represent that with the tiny little letter delta. So this is a Greek letter delta with a minus or a plus to let us know if it's a partial negative or a partial positive charge. The other thing that I want you to remember is that dipole-dipole forces are not a full bond. There's an attraction between one end of one molecule and one end of another molecule, but while it is strong, it is not a full covalent or ionic bond because these ends are only slightly negative or slightly positive. Okay, let's take a second to look at this picture of a dipole-dipole bond, and I'll give you an idea of what I'm thinking here. This little Pac-Man circle is a representative of that intermolecular attraction. It's not solid because it's not a bond. This is a covalent bond between hydrogen and chlorine, and it's a polar bond because the electronegativity of chlorine and the electronegativity of hydrogen are different. So because of that, what happens is our hydrogen has this little delta positive and our chlorine has this little delta negative. And because one end is partially charged positive, one end is partially charged negative, they have an attraction to each other. And it's not like magnets, but we use magnets to kind of create our like our metaphor for what happens. It's an electric attraction. The other thing that I want you to remember about dipole-dipole forces is that they're stronger than dispersion forces. So dipole-dipole forces are stronger than dispersion forces. Let's go talk about what happens when we have hydrogen bonding. We're going to go back to the example of water that we did in IMF 1. And I want you to think about really quick where all of the delta positives and the delta negatives go. And I'm just going to go ahead and write that for all of my oxygen and hydrogen bonds here in these waters. Okay, I went ahead and I added those little deltas, and you can see the little Pac-Man dots on all of my intermolecular attractive forces. Remember that the little Pac-Man dots represent a strong attractive force, but they aren't a bond. The only bonds that are present here are the bonds, the full bonds between oxygen and hydrogen. So I'm going to go ahead and draw those in, just so that you can see what I'm talking about. All right. So remember what I said was that hydrogen bonding is a very special kind of dipole-dipole force. And hydrogen bonding happens when I have an attractive force between hydrogen on one molecule and fluorine, oxygen, or nitrogen on a different molecule. So in this water, I have hydrogen on one end, oxygen on the other end, and there's an attractive force between these two. Let's go ahead and write the definition. All right, I went ahead and I wrote the whole thing down, and you can always pause this video to write this down for yourself if you haven't already, because we did take this note in class. So hydrogen bonding is a special kind of dipole-dipole force that happens between hydrogen on one molecule and the oxygen, fluorine, or nitrogen on another molecule. So those are the three that I want you to know and remember is dispersion forces, dipole-dipole forces, and hydrogen bonding. Dispersion is the weakest, and hydrogen bonding is the strongest kind of intermolecular force. So I put them in order from weakest to strongest. What we're going to do the next time we meet is we're going to practice classifying what kinds of intermolecular forces are present in a molecule. So to be able to answer that question, I'm going to start by helping you make a flowchart to answer the question. A flowchart is a kind of choose your own adventure. So I ask a question, and depending on if the answer is yes or no, you move to a different part of the chart. So the first question that I need to be able to answer to make a determination of what kind of intermolecular forces are working is to ask the question, are my bonds polar? We're going all the way back to the beginning here. If I answer this question no, then the only kind of intermolecular force I can have is dispersion forces. Why? If the individual bonds are polar, why is intermolecular force only dispersion? If the individual bonds are nonpolar, then the whole molecule is nonpolar. And if the whole molecule is nonpolar, then the only kind of forces that we can be having are dispersion forces. Let's think about what happens if we answer the question yes. Remember the example of the NH3 versus the BH3. Both of those had polar bonds. One of them had a BH bond, the other one had NH bonds. One of those molecules was polar and the other molecule wasn't. So that's the second question that we have to answer. So even if the individual bonds are polar, that doesn't mean that the whole molecule is polar. For a review of that, go to the other Edpuzzle or the other video. If the whole molecule is polar, it has a dipole moment. So if I can answer yes to is there a dipole moment, then I can determine whether or not I still have to keep going on my flowchart. So let's imagine that we answer this question no. So we'll go back to that idea of BH3. If there isn't a dipole moment, then the whole molecule is nonpolar. And if the whole molecule is nonpolar, then the only kind of forces that are present are dispersion forces. What happens if I answer this question yes? If I answer this question yes, then the next step is to figure out if I have dipole-dipole forces, or if I have that special kind of dipole-dipole force, like H and F, O, or N. So I'm going to ask the question, is HFON a thing? H-phone. All right? If I have hydrogen and fluorine, oxygen, or nitrogen, then I have hydrogen bonding. Okay, so if there's hydrogen and fluorine, oxygen, or nitrogen on my molecule, then I have the possibility for hydrogen bonding. If not, then the only kind of force I'm dealing with is dipole-dipole forces. So let's go ahead and zoom out or back out. I have to answer first, are the individual bonds polar? If not, then the whole molecule is nonpolar and I only have dispersion forces. If yes, then the whole molecule might still be nonpolar. But if the molecule is polar and there is HFON, then hydrogen bonding is the kind of intermolecular force I'm dealing with. And if it's not, then I only have dipole-dipole forces. That's going to be it for this video. When we get back together, we're going to practice using this flowchart for several different molecules. And we're going to figure out what kind of forces are being present in those molecules. Have a great afternoon, and I will see you on the next one.